find very trying to find very weathered outcrops because Africa now really sits in the equatorial belt, laterites and things like that. So finding a good outcrop is not easy. So this work has really relied an awful lot on the last 20 years of oil and gas exploration, drilling into the subsurface. And for instance, in the East African rift system, you can see what's happening in the Pleistocene. You really can't see anything in outcrop. It tells you what's happening before that. So you need wells to do that. But I mean, despite this, this lack of outcrop geology, the one thing really that Africa has given to the world, along with South America, is plate tectonics and continental drift theory, because it was long noticed that, for instance, this Cape Fold belt that we're talking about in a minute came right across. This glacial sequence in the late Carboniferous came right across. Other things such as granites came straight across. And of course, long noticed that South America sat nicely in this elbow of the Gulf of Guinea. That was really very basics of plate tectonics and continental drift. Now, everyone mute, please. So, in many ways, Africa is the central piece of the jigsaw of plate tectonics. And in fact, we know what happened to Africa. We know 90% of what we call the conjugate margins of the plates that were joined to Africa very well. The areas of really dispute are down here, particularly the position of the Falklands, and up here, the Eastern Mediterranean, the timing and the actual fit of the eastern part of the Mediterranean. But apart from that, we know the jigsaw pretty well. I mean, the other thing is evolution. Oldest known life, 3.5 million years in South African, obviously Precambrian strata. Major expansions of life. The one that really stands out is the Carnian, what's sometimes called the Carnian wet period in the Triassic, when it was thought that, I mean, some people think that life evolved steadily, a number of species grew steadily through time, but this Triassic period really debunks that, really says there was an explosion of different sorts of life, insects, dinosaurs, you name it, at that time. And that, again, is located in this Multeno Formation in South Africa. And of course, the explosion of life most recently, which led to us. Everyone here in geological time is a recent immigrant from Africa. There's more diversity in the human species in Africa than the rest of the world combined. So that's clear. And that is actually, that story I probably wouldn't have time to go into today. The migration of hominids out of Africa seems to be very much linked to climatic changes in the Pleistocene of Africa, which drove people to migrate northwards in search basically for water, eventually leading into other continents. And finally, tectonics. Really, 90% of African tectonics is extensional, in other words, rifts. The only parts of Africa which see fold belts and compression are the north, mainly in the Tertiary, and the south in the Permo-Triassic. The rest really, apart from things like inversion structures, don't really have anything you would call an orogenic belt. So there's lots and lots of these extensional periods. It's not just East African rift system, there's about 12, 13 of them. So, brief word about the Precambrian, because really you can divide African geologists that study Africa in two: those who look for minerals, who look at the Precambrian, and those who look for oil and gas, and perhaps more recently for geothermal and things like that as well, which is mainly concentrated in the East African rift system. We look at the softer rocks from the Cambrian onwards, and so they don't interact very much, these two. But in fact, in many ways they should, because essentially during the Precambrian, particularly the later part, we saw all these red areas, which do play a very important role in delivering coarse sediment sandstones to the margins of the continent, which contribute the oil and gas reservoirs, but also the lineaments that really formed when these cratons combined with each other to form the first elements of Gondwanaland. And essentially, you can see there that that lineament is Precambrian, but that will control the East African rift system. So these lines of weakness are very important, and they're repeated several times. I mean, for instance, this one in Tanzania, there's something like 5 different rift sequences developed on that repeated extension in the same place. I won't really say much about the Paleozoic because the emphasis really is on the breakup sequences, what we call the Wilson cycle of starts with the extension in the Permo-Trias and leads to present day, which but there was a previous Wilson cycle from this event that combined all these cratons, which led to this mountain belt in brown here, which is we call the Pan-African. It's actually several mountain belts, not one, of different ages. These mountains were extremely high as the Himalayas at least. And of course, there was no vegetation around at this time. And so the debris from this mountain belt went everywhere. And the world's largest clastic sandstone deposit is the Camber-Ordovician sandstones, which were fed off here and really extend all the way over from the Middle East, right over into Nova Scotia and America. Absolutely, thousands of square cubic kilometers of sandstone. Very layer cake, very correlatable, which is not what we see in the later part of the geological record. One of the reasons I haven't done too much about the Paleozoic is that there has been maps already published for it, which is rather strange. There has not been maps published for the whole of Africa for the Mesozoic or the Tertiary, but there has been for the Paleozoic. So we start our story in the Permian, and just to orient ourselves, this is really the map we saw at the start, the edges of the African plate. Each edge has a different age to it. It goes from probably around Triassic here, late Triassic, to today in the Red Sea. So these margins are of just every age between that. And in fact, it does seem to follow a pattern. It seems that we start here in the Permian of Arabia with what's called the Neothethian Ocean, go through here in the Triassic, through the early Triassic, early Jurassic through here, along a big transform, again, early Jurassic through here, and eventually into middle Jurassic in what was the Proto-Caribbean Ocean, not the present-day Caribbean Ocean, but previously an old ocean that's been consumed. So that was all, if you like, sometimes called unzipping that way. And the second big trend is really going like that all the way around to eventually connect with this one, which started in the early Jurassic here, at least in terms of the first oceanic crust, again down through middle Jurassic, and then into earliest Cretaceous, through the early part of the Cretaceous, until we get to the final departure of South America in the Cenomanian, and we link up then with the older ocean of the Central Atlantic. So, the Central Atlantic is older than the Southern Atlantic, but the Southern Atlantic actually youngs northwards to eventually combine with it. So every age of margin really conceivable, and every type of margin conceivable. There are what's called hyperextended margins, which are really rifts with extreme extension on them. There's transform margins, which are San Andreas Fault times California margins of where essentially it's moving sideways against another continent. And there's an awful lot of what's called volcanic margins, which actually are the commonest, which are essentially the tens sometimes of kilometers of what are called seaward dipping reflectors, which are essentially subaerial lava flows, which erupted before the actual breakup occurred. So it's really anyone who's interested in continental margins, for instance, you can look at how the heat flow compares with the different ages of the margin, with which ones have the volcanics associated with it, which ones don't. So it is a veritable laboratory, these margins. It really is the theme of this talk. So essentially, we're starting in the Permian, and of course, just to go on through some of the colors on these maps, these browns are fold belts, and we're still in Hercynian Moriscan here. You'll see these rapidly dying away, coming back a little at present day in North Africa. There is a major fold belt down here at the time.
No, you're not unmuted.
No, unmute me because I'll.
Yeah, which is the Cape Fold Belt, which we have a little picture of just to break things up. But apart from that, essentially the reds, which you'll see really taking off in the Cretaceous, are rifts. So at this time, there is a major rift system, and I actually think this reds now come down here now and eventually come up against this mountain belt, or essentially a bend in the mountain belt, which starts to make sense because then these rifts seem to be controlled by big wedge faults, and they're very narrow, very steep. At this time, again, we're seeing the Hercynian tectonics are dying out. It's active down here. There's an ocean between Patagonia and Africa, which is closing, a back arc that's closing, and that will eventually close completely to suture Patagonia against Africa. Of course, it's going to go away again, but we'll see later. There's this large shear system which actually pulls these rifts open. Some of them are very narrow, some of them are inverted, others are oblique to it, which are just pulled open by that system. We call these passive rifts. The other thing really is down here, so this symbol here is coals. This is about the only really interval of a lot of coals in Africa, simply because this is about the only time, at least in Mesozoic times, at which we had a cold climate here. So we had peat bogs, because the South Pole currently sat in Antarctica, which is sutured to Africa, and the equator was up here, more or less over Spain at the time. What you will see and what follows is that the South Pole moves relative to Africa this way. Of course, this is Africa moving relative to the South Pole, but that's not how I've portrayed it. The dots are what we call internal sinks, which are non-marine strata, fluvial sandstones and the like. The blues here are marine sediments on the shelf of marine sediments. This is clastics, and this is carbonates. And you'll see an awful lot of carbonates, particularly up in this area, really caused by one of two things. One is the climatic belts, because they're generally the main and fairly arid belts throughout their history, and also because the distance from high topography, which means very limited clastic supply. Carbonates grow in very clear water, and if a lot of clastics come in, they tend to kill the carbonates. So that's the main colors. We'll see others. I mean, you can see the paleolatitude belts here, and you'll see comments on climate, which will generally become a bit more numerous, and that's extracted from the literature. We'll also later on we'll see things like evaporites appearing and things like that. Perma-Triassic boundary, and of course this is the start of the Mesozoic, which is really which is really marked by something which is not in this map at this time, which is the basalt eruptions in Siberia. We will see big basalt eruptions, what we call large igneous provinces, to follow, which define some of the other main geological boundaries in time, but not in this map. Now again, really the South Pole is still sitting down here at this time, warm, temperate. It's getting a bit warmer. It's getting a bit warmer, but still in much the same climatic belt. So there seems to be a warming across the Earth at this time. It's not a simple case on these maps that the climate responds to the latitudes. The relationship of climate to latitude does change, and particularly you'll see on this and the following maps is huge arid areas, even going over the equator. And there's nowhere today that it's arid on the equator, but it's very difficult to get away from the conclusion when you see things like evaporites that it was arid on the paleoequator in the Triassic. Now at this stage, essentially, we are moving marine waters in this way, but it's not oceanic crust yet. Essentially, so this trend you'll see will eventually bring marine waters all the way through down here and then into the Caribbean, Proto-Caribbean. The main tectonic activities, really, this is the peak of the Cape Fold Belt, which those of you who have any links to South Africa will know very well. Again, there's only fold belts in Africa in the extreme south of this age and in the north, Tertiary age. That's the only fold belts we have. There's also things happening in here. These are platelets that will eventually become Iran. They go off into the Tethys Ocean and come back again as Great Zagros Mountains. And it looks like the breakup of these platelets is allowing some marine waters to come along and invade some of these earlier rifts. And that marine influence is very concentrated in Madagascar. We don't see it almost at all in the main part of Africa, really because Madagascar is the closest area to where this breakup of Iranian fragments is actually occurring. Now the rifting has moved a bit north. It was mainly down here before. It's now moved a bit here. To some extent, this is a precursor to the opening. There'll be another phase of rifting in the same areas in the early Jurassic, which will precede the opening of parts of the Indian Ocean. So this is a Cape Fold Belt, and the structures, I mean, very common in Europe. We're very used to compressional tectonics right across Europe. You can see structures down this in Bude, Bay and Cornwall, and the like, which is Hercynian, which is not that bit older, but not that much. But this is the end of it. It doesn't happen again. There's been a huge amount. This is semi-metamorphic material. So there's been a huge amount eroded off this stuff throughout geological history. And it's certainly in petroleum geology, understanding what has been eroded at different times is very, very important. And we'll talk about that with respect to what actually was the largest oil discovery in the world this year a bit later. Now we go into the Carnian, and it's actually, this is one of the most bland maps. You might not think it. When things become a little dashed, that's when I'm saying the rifts are not so active. They're dying a bit. They're still moving. They're relaxing a bit. There are things happening up here, and this is a precursor to this margin opening. So really, again, this is rifting. It's still rifting, and that symbol there is an oceanic ridge. So I think the oceanic ridge, I mean, there's a lot of debate over this because we can't see magnetic stripes. There's too much sediment. And so you're dependent on indirect indications of geology to tell you what was oceanic crust, when rifting was occurring, when the spreading was occurring. But I think it's got about as far as the Israel-Lebanon border at this time. It's rifting beyond that, and it's going to split further. And it's now rifting all the way down to here. So arid, again, the words hot, there are bits of hot, humid material, but generally the word arid almost over very, very wide belts at the time. Now, of course, we're a long way from the ocean. We're the center of Gondwanaland. Any wind carrying any moisture has got to carry that moisture an awful long way for it to form as rainfall in Africa. But even later, when we see ocean form here, it does still stay quite arid. At this time, we've got major fluvial systems forming, and this is actually one of the big gas-bearing reservoirs in Algeria. This movement of Africa relative to the equator, from now on, it's going to get a bit simpler. The equator's here. Now, today it's there. So all Africa is going to do from now on is actually tilt a little this way. So that big movement of the South Pole, which is now down around, let's say, way off the map now. It's gone down here. That movement of the South Pole through the Permo-Triassic, which contributes to very rapid climate change, has actually ended. And so we will tend to see the same climatic zones, or we should tend to, might expected to see the same climatic zones that we see today. We don't necessarily really. There are periods that seem to be particularly arid, areas that seem to be particularly wet. And I don't think these things are terribly well understood at this stage. Now these rifts are dying a bit. They're eventually going to, this bit will reactivate a bit. And this is when we have down here this Continental formation, which is one of the big explosions of life, one of the big evolutionary steps. Now this is disputed. Some people think evolution was a long, gradual process, that there was a steady increase of species through geological time to today. But the Continental formation is actually the argument against that actually there were explosions in the Cambrian, which of course people in the Red Wing Geological Society have heard about. There's other explosions at different times. It tends to be more of a step process. And actually there was some people think there was almost as many species around in the Continental formation times in the Carnian, which was a period when it was wetter for a short period than there is today. Jurassic-Triassic boundary, like most of these boundaries, it's a large igneous province when essentially there was big volcanoes going off, spewing large, horrible things into the air, which killed an awful lot of life and killed a lot of the species which pre-existed. I mentioned the Permo-Triassic boundary in relationship to the Siberian trap basalts. And here it's on the map. The Jurassic-Triassic boundary is actually these purples here with the V's in them, which are only the erosional remnants of it, of course, because they're originally much more extensive than that. And this is what we call the Central Atlantic magmatic province, the core, and it's a plume rising from the mantle, precedes the breakup, very short-lived. Generally, these things are 2 million years at the longest. There's a major mass extinction associated with it. It also roughly forms the end of the rifting. And next map, you'll actually start to see the Central Atlantic opening. The Tethys, which I think is a better term than calling it the Mediterranean. Some people just call it the Eastern Mediterranean. I think it's gone a bit further here. Can't really tell for certain, but it's sometime around here, going into the earliest part of the early Jurassic. Eventually, it'll also open this little bit in here, which is the Ionian Ocean, and these will combine. And we'll then have another ocean formed up here and another ocean formed up there. So things are spreading slowly westwards in that trend. The East Africa is actually not doing anything this time. It's sort of the calm before the storm. It's going to rift in a minute. The previous rifts have died. They're failed rifts rather than successful rifts. But we'll now see another set of rifting forming. And again, very surprisingly this time, it's arid. And that goes against what a lot of paleoclimatic modeling says in this area, because we're now getting not so far from the oceans now, particularly down here. And yet, if anything, in South Africa, it actually gets more arid from the Triassic into the Jurassic. And that's against what most people would expect. So geology has got this habit of confusing us and not doing what we think it should. Right, now a little light relief here. Let's go see now we're going to start to see continental margins formed. So essentially, just run through, this is Colin's PowerPoint movie, and it goes from the early Jurassic, 180 million years, to today. So that's where we are today. Now, if you look, I think, go back again, essentially, and then get back to where it was, we'll start to see that 180, first margin that goes is this one. We don't have the Tethyan margins on here, apart from this one, and then the East African margin goes, and then it comes around to here, and gradually goes up here, and it's gone faster than my speech there. So we'll come back and just show this for the South Atlantic now. So we're going back to roughly 130 million years. So let's get about 130 years. You'll see this first part of the South Atlantic opening, which is just a little bit of Cape Town. And then it gradually, watch this red line, increases quite rapidly and eventually combines with the Central Atlantic. That is really how they break up the thing. And finally, not on this chart, is actually which should be here, is actually this breakup here in the Red Sea, which is happening today. So again, breakup of any age that you can conceive of, from some of the oldest oceans in the world to the youngest oceans in the world. So the first bit is apart from this, which wasn't on that thing, the Ionian Sea, going into this big transform. There's two big transforms. And actually, most of Africa is a transform margin, which is something very much not appreciated by most workers in North Africa. These are big transform faults, and here, and then the sea was spreading here down to roughly here. And at this point, it actually goes off in the transform into the earliest Gulf of Mexico rifts. And I think there's quite strong evidence for this. It's been picked up by a number of papers that this bit of Senegal and Florida is actually younger than the rest of the Central Atlantic. So again, it's part of this trend, really, things getting younger this way. It's very slow at the time, and for start, initially it was thought that the breakup was actually younger than this. Again, breaking up here now, still spreading, and this is forming what we now know as the Eastern Mediterranean. Now, the Eastern Mediterranean is much, much older than the Western Mediterranean. You will not see this happening until the Tertiary. But another of these big lips, large igneous provinces, not such a big extinction this time. There is one. It leads to an anoxic event in about 180 million years. This actually goes all the way to Tasmania, this one, but these are called the Karoo volcanics. And a bit light relief here is that these form Victoria Falls. And Victoria Falls has been in existence for 5 million years, which is quite a long time for a volcano, for a waterfall. But it's not been in the same place. It keeps on going back. The first Victoria, these are fracture systems within these lavas, which were erupted at this time. And essentially, these are all generations of Victoria Falls. Today it's here, but it's actually about to go and go further back and to exploit these fracture systems further back. Now, but some of you will know that actually what this is gives this very lovely zigzagging pattern, which is supposedly the best whitewater rafting in the world as a result of this. A lot of this 5 million years was also related to the propagation of the East African rift system into this area as well. Now, here's a gallery map that looks relatively uninteresting. This is a feature, really, that there are periods, and this is not just Africa, it's global. There are periods when not a lot is happening in the world, and there's periods with an awful lot is happening. You'll see the difference between this and the next slice. We have got some things going on, but very little rifting. The things are essentially, we've now opened the Indian Ocean. It's basically oceanic ridge in here, oceanic ridge in here, with a big transform called the Davy Fracture Zone in between. And so West and East Gondwanaland, which is West Gondwanaland, South America and Africa, and Madagascar, India, Antarctica, Australia, which is East Gondwanaland, are separating along here. And eventually this will go down into this here. These rifts are precursors to this bit opening in here. This is one of the most controversial areas of plate tectonics. Where did the Falklands actually sit? I think from looking at stratigraphy, they must have sat in this position. I won't have time to go into that. Other people think, looking at tectonic belts, they sat up here. But really, you can't make the plate. Can't get things in the right position of the two of Falklands relative to Africa, because you see deep marine strata in here and deep marine strata in there. So if you put the Falklands back there, you can't you can't bring in the sea to the basins in South Africa. So I quite strongly believe that the Falklands sat south of South Africa and not over in this position, which again, this is something that geologists love lobbing weapons at each other at conferences over. This is getting quite wide now. It's going into the Caribbean. Again, a lot of arid climates, high sea level at this time. This is a time of very high sea level, and you see a lot. This blue pattern here is actually not oceanic crust. It's off-shelf sedimentation, deep marine sedimentation. It's only really oceanic crust where you see it going over one of these blue hatched lines here. But though in fact it is actually oceanic crust in here at this time, but the spreading now dies. Eastern Mediterranean spreading is over at this time, and now instead we're spreading the Alpine Ocean, sometimes called the Piedmont Ocean. That will eventually become the Alps. So that ocean again doesn't exist anymore. It's been consumed just like the Proto-Caribbean has. Now look, contrast that with this, rifts everywhere. So this basically looks like somebody has put their hand on Arabia, and somebody's put their hand on another person, put their left hand on South America, and has just pooled. It's basically how this looks. And you then get wrench faults appearing perpendicular to where that tension is, and you get rifts perpendicular to these wrench faults. So it looks that the whole of Africa was under some form of tension at this time. The climate's completely changed. It's now a lot wetter. It's all of a sudden, it's become a lot wetter since the previous period. We're now starting to see topography form, which is what's up here. We've actually got this enormous delta of Morocco, southern Morocco, which is actually the second biggest delta and fan system, deepest center that Africa has ever seen after the present day Niger. It's bigger than the Congo, bigger than the Zambezi. So something, this topography. Now, the way I've calculated this topography is A, when you start seeing high sedimentation rates, it must be high. And B, look, if you look at these things here, these are indication of what's called appetite fission track analysis, which I won't have time to go into, but it's looking at radioactive tracks within the mineral apatite, their lengths, and the number of these different lengths. And from that, you can deduce the ages of uplift. So, for instance, suggestion is that these ones here, that the southern part of South Africa is going on here. Now, again, as we said before, these purples are volcanic. So this is a volcanic margin here. Also, these seaward dipping reflectors, and the southern part of the South Atlantic is now opening, but it's only rifting in the northern part of the South Atlantic at this time. In many ways, these rifts really just very similar to these ones, except these ones will die. These are failed rifts. These ones will actually become oceans. And also we're starting to see a lot of the wrenching is through here. That will actually control the eventual opening of this margin of Africa, which is a wrenched margin. But it starts in quite a sort of haphazard fashion with little bits in here, little bits in here that will little bits in here that will eventually combine with each other. And another big wrench fault through here, which is the Agulhas fault, in which this is opening. And so that's basically the story at this time. There's a lot of tension, and you almost feel like you're pulling a bit of paper apart. Moving into the Aptian, again, now essentially this gets quite wide here. And we actually have a volcanic ridge here, which ponds, this color is salt. We saw a lot of salt earlier as well in this interval, in here, in the latest Triassic Pliensbachian and we'll see a lot of salt again in the tertiary parts of the tertiary. Salt obviously is an indicator of evaporation. So again, an arid climate. It really is the commonest climate type we actually see in Africa. Now, and a lot of wrench faults up here, which seem to somehow tie to what's happening in Europe. because we've seen the first what's called Alpine events, and it's only in the Eastern Alps, not in the Western. Western Alps is still an ocean at the time. It does seem that these wrench faults are somehow, I don't know how yet, transmitting through this continent, Adria. Now we know from paleomagnetic wandering curves that for a long time, Adria was actually joined to Africa and was moving with Africa. Obviously, it's not now, but in many ways, and I'm sure you've all heard that the Alps is the collision of Africa with Europe. What it actually means is the collision of Europe with Adria, and Adria was at times part of Africa. The other interesting thing, I think, we're starting to see the first signs of uplift in South Africa. Now, the world's largest area of topography, which is not volcanic, not orogenic, is South Africa, the South African plateau. Johannesburg, you probably know, is at 5,000 feet of altitude, and it's dead flat. That was a step-like process. We'll see in a minute. There was several stages of uplift of that, but the first bit was in here against the Cape, and it seems to have been caused by this was still part of South America here. So in fact, the last bit of South America to leave here, which is called the Morris-Ewing Bank, and there's a lot of inversion in here and wrenching along this Agulhas fracture zone, and that seems to cause the first uplift here. The interesting thing is that this little yellow here, the yellows are delta fan systems, sandstones. And that's really what people in the industry look for, the best reservoirs in deep water. And that caused a switching in the earliest Albion times. Immediately after this essentially brought river systems were brought, which originally drained this way, were actually now drained until northwards. And the very first sand to form in the Orange River has currently had, just in the last couple of months, has had what seems to be the biggest oil discovery in the world this year. Now you might ask, why we're still exploring for oil. Well, some companies are, some aren't, of course. It does involve a little bit of an argument here because this is in Namibia, and it's the first oil discovery in Namibia. And the Namibians, of course, will say, well, why can't we develop our oil? You, Britain, have developed all your oil, and you're all rich because of it. So why can't we develop our oil? So this is a big dichotomy, if you like, to do with oil and gas exploration. Like I say, we've got big salt basin in here, enormous thicknesses of salt in there. Madagascar stops moving now. This ocean dies, and eventually you'll now see it splitting off from the Seychelles and from India. Moving to the late Albion, the upper part later Cretaceous. Now, really, what happens here is the last at this point here, and at this point here, that's the continental ocean boundary, that line there. So that's the continental ocean that lived in the African plate. That's the limit of the South American plate. This is last contact between Africa and South America, and that's scraping together the continents seem to be creating this high in here, and essentially that long line of transforms has now become oceanic transforms, and some of these are, of course, are still active. There's still earthquakes today in Ghana along a lot of these, and there's a long continuous transform from there right into almost to the Red Sea, which is controlling these rifts in here in Chad and Niger and in Sudan. The late Cretaceous really is another one of these episodes in which an awful lot seems to happen. We sometimes call in Africa, we call this the Santonian squeeze, simply because, as I said several times, compressional tectonics is quite rare in Africa. But at this time, we see all these browns appearing down here in what's called the Benue Trough, Nigeria, here in the western desert of Egypt, in the first phase of compression in the Atlas, and even bits down here in areas like Somalia are showing signs of compression. Now, again, you don't really see why the way I've drawn these maps, because what's happened is that Africa has actually moved relatively little through the Jurassic and the early part of the Cretaceous. And at 86 million years, it takes a sudden kink and starts heading for Europe. And what's the tectonics from now on have been likened to a boxing match. between Europe and Africa, with Europe having a very strong right arm and a weak left arm and nothing in between, because in between we still get rifts. Here we get mild compression. It's really just folding. It's not orogenesis. It's not reverse faulting. It's just really inversion of old grabens. But here we get more complex tectonics and actually see things like folding and nap formation and things like that. So Iberia is the stronger punch than the Turkey is, if you like. Now, shortly after this, we'll start to see the Eastern Mediterranean start to close. Now, we still actually don't have an ocean in the Eastern Mediterranean, but that's going to appear soon. At the same time, I mean, an awful lot of things happen in Santonian. One of the other things about it is the peak of kimberlites. So it's the peak of diamonds. How on earth is that related to the collision with Europe? But it's at the same time. And it brings out surges of sandstones, of course, which are often targets for oil and gas exploration. So this pulse to the planet, if you like, is just something that I think we don't fully understand in geology. Now into the Tertiary. So this is more now you're really seeing Africa looking like Africa, because South America's gone away now, India's gone away, Seychelles even is in its current position, Madagascar is in its right position. Okay, this is still to form here, and lots of things are going to happen in here, because we've got this subduction zone which is subducting the Alpine Ocean. It's actually now just the very top of the map starting to form the first parts of the Alps, and as Adria really collides with the main part of the European platelet. But what will happen is eventually this little plate in here, which some people call Alcapeccia, will actually go off, will segment into 5 pieces and become Calabria. It'll become Corsica, Sardinia. It'll become the Kabylias of Algeria, and a little plate which has actually sort of been foundered in the middle of the Mediterranean called the Alboran plate. And that, as it opens, will open an ocean behind it, which is the present day Western Mediterranean, which I think is going to be quite short-lived. I think that's signs of it starting to subduct already. That's the general story throughout this European area of short-lived oceans. Now, the not much happening tectonically at this time. It's almost a low tectonically, but a lot happening down. In the later part of the Cretaceous, we've seen a lot of topography form down here. We've seen the first signs of volcanics here. Now it's going to come widespread. This is really the start of the tectonic cycle of the Red Sea and the East African Rift System. The other thing about things, all these Bs are bauxites. This is a climatic event. Bauxites tell us that it was warm, humid, and very slow erosion. And we're seeing the bauxites throughout just like previously, we saw arid conditions throughout the continent. We're seeing humid conditions throughout the continent. And of course, in this country, we're seeing the calcretes and the sarsenstones, things like that. So it was also pretty warm here. So there's a major expansion of humid tropical conditions at this time. And it seems that almost all of Africa, apart from a little bit down here, was in the tropical zone now. Despite it, the tropical zone was going from 0 to 40 degrees. So the one thing I meant from now onwards is that this is the time when these bauxites were cut. We start seeing the cutting of these surfaces. And again, probably the story is a lot more complicated than I'm going to pretend it to be. But generally, when we see mountains in Africa, just like we do actually in the Cairngorms and Norway and in Wales, they've got pretty flat tops. They're not peaks. Well, Kilimanjaro is a volcano, of course, that's an exception. But I mean, what often is the case, I mean, if you can put these two photographs together, down here is that surface which the bauxites in it, which was cut sometime around Eocene times. There's an older surface which was cut in Jurassic early Cretaceous times called the Gondwana surface, that's the Lesotho border with South Africa up there, the top of the Drakensberg Mountains, and it's flat. And then below it, again, another escarpment. So see, this is the general African topography, flat with escarpments. And most erosion is actually horizontal, not vertical. It's the retreat of these escarpments, which helps us a lot with understanding what's been eroded at different times. So a lot of, people are trying to see what's eroded at different times, where's it supplied to, could that be a reservoir like that, like that Venus discovery in Namibia. Now, eventually we start seeing Alpine now. This is really the Alpine proper, Pyrenees, Alps proper, Atlas Mountains. As you'll see here, the Apennines are a bit younger than that. So we sometimes call this the Pyrenean event. Essentially, volcanism down here, things are now start some rifts, which go north-south, but not really much at this time. And we go to the Oligocene. This is really, Oligocene is when topography in Africa starts to look like the topography today. These highs, for instance, did not exist on the previous slice. It was flat at the time. We know that because essentially these carbonates were coming a long way in to Africa. No sign of any clastic input. So it has to be pretty flat. The transgression coming in means topography less than 200 meters, because even if you melt every glacier in the world, you only get 150 to 200 meters of sea level rise. So you can see something about the topography when you do see these carbonates coming a long way in. The carbonates are retreating now, and you see this topography created. And these swells, which is what they are, they're sort of semicircular, and they seem to be swells of the mantle. They're mantle related. They are associated with high heat flow and some mantle derived volcanics. So they're quite different sort of topography than we see in this country, related to orogenesis, etc. This is getting bigger. This essentially, if you look at that arrow there, tends to suggest that the northern part of the South African plateau is going up at this time. And that means we start to get drainage systems, these rivers, which I haven't been pointing out to date, start to look like the rivers today. So, okay, the Niger was actually there from about the Paleocene. The Nile forms today. There was no clastics here. Nice form of the Oligocene, sorry. The Zambezi takes a big pulse. It was there before, but it's quite short. The Orange River is dying a bit because of an increase in aridity in this area. This area starts to get very arid from now on. But now things are starting to look a lot more familiar. So we see something like the Nile River. Now it's the longest river in the world, but it's actually not even the most sediment-rich river in the Mediterranean, which is the Rhone, which is a much shorter river. And the reason is it's hyper-arid. It's desert. The present Sahara Desert, and there were precursors to it, started about 2.5 million years ago. And so there isn't anything, all this is desert in here. Practically all the sediment and it's coming out here actually comes from Ethiopia and is volcanic derived at this time. But if we go back in time to the Pliocene, actually, at this time, it was very wet in here, and actually there was a big monsoon coming in from the Indian Ocean. So we're seeing all this area was wet at the time, and there was big erosion of these highs taking place at the time. And so these circles in here, so maybe we should have pointed out by now, are sedimentation rates, high sedimentation rates. We're actually getting much more sedimentation coming out the Nile in the Pliocene. And indeed, the same is true in the Niger. There's more sediment coming out in the Pliocene. And that's a function of the fact that the climate was wetter then than it is today. And before the main part at least of the Sahara Desert formed. Now the other aspect is really we rift here. We start to bring oceanic crust through the Gulf of Aden, and that will eventually start to go up through here about 5 million years ago. And this eventually, about this time, we start forming the Dead Sea Transform. So now, for the first time, Arabia is a separate plate. Up to now, Arabia has been part of the African plate. And since I always say that since all the oil and gas reserves are in older strata, on the Arabian plate. Then when it was part of the African plate, that makes Africa the most hydrocarbon rich plate in the world. So today, essentially now we're starting seeing a lot of this topography actually still very young. But this topography, even the Alps, is Pliocene. So now this is when we're really, and there's Zagros as well coming in now. The interesting thing is that the East African rift system, which is now, most of this is Pliocene, very young. It started off around here, going to about here in the early Miocene, over here in the mid Miocene, and down here. And you'll see in the next map, it's actually gone down here. So again, it's this unzipping. And will it become an ocean? Don't know. Maybe at that time. Lots of volcanics, obviously, now in East Africa, and this is the basis of the main geothermal resources of Africa in that area. Currently, all geochemical production actually is in Kenya. All geochemical production in Africa is in one country, which is Kenya, which is something like the 5th most important in the world. So this is coming up here, eventually leading to the splitting of the southern Red Sea and rifting in the northern Red Sea. And the East African rift system essentially is so young that we see the topography of the rift shoulders today still forming. This is one of the rifts in Tanzania, the southern end of the eastern branch. It's the model rift system. It's the best studied rift system arguably in the world, simply because it's happening today. And now really the situation today is it's now gone through here and it's now going off this way, and may eventually, and some people, particularly Mike Daly, I don't know if you heard his talk, president of the society, he actually now calls this the sand plate, and he thinks that this is the start of this leaving Africa, as well as what's called the Somali plate and what's called the Victoria plate through here. And we now call this what's left the Nubian plate. So perhaps this Red Sea was the start of Africa segmenting. Climates, of course, are all over the place in the Holocene and Pleistocene. Rise and fall of the pharaohs follows a humid cycle. The migration of mankind from Ethiopia northwards follows a climatic cycle. These are actually Milankovitch cycles of about 200,000 years. So there's no way I'm going to be able to produce a map for each of these. But that's really going into other subjects. And where it's going now, I mean, obviously, eventually this will be, oceanic crust has got to here. In the middle part of the north of the Red Sea, there's actually an island in the northern part of the Red Sea. You can see mantle actually outcropping, which is what happens on hyperextended margins. You actually exhume parts of the mantle close to the continental ocean boundary. Obviously, the Dead Sea Transform is active today, so it's going to take Arabia further off. And is this all eventually going to split off, as another continent or as a series of continents? The Atlantic obviously is continuing to widen. The Eastern Mediterranean is disappearing. That started in about Oligocene times. It's essentially that's what's controlled things like Santorini, all the fact that Turkey is a major earthquake area. And there's signs from volcanics, from complex volcanics, that actually the Eastern Mediterranean, which I said is a much younger ocean, is actually maybe starting to subduct below Africa. So it may be quite short-lived. So come back in a few million years' time and let's see how things look. Okay, that's it. You want to take back control? Have we got? Can't hear you. Do I have to give up control, do I? Right.
Thank you. Yeah, no, yes, if that would be okay with you. I won't stop recording just yet in case there's questions that it's okay. So if anyone has any, please feel free to mention them or put them in the chat. But thank you so much, Duncan. That was really, really interesting. I suppose just as a general question about how do you go about mapping and putting together all of that information to create such detailed analysis, basically? Like, there's such a large history there.
Oh, you don't reinvent the wheel. For instance, I mean, can people if I'm still
see
screen
your
sharing, so you can still see the tectonic map. So if actually, I mean, for instance, the tectonic analysis, there are starting points here. Now, I mean, I published myself mainly in this area. So, for instance, I'd initially started this project probably a decade ago. I didn't realize I was starting the whole of Africa, but I was starting on the East African Rift System, and I published on that. And I did the Permian-Triassic Rift System, Jurassic Rift after that. So that was my start. And then I eventually found some people who put a tectonic elements map together from North Africa, copied it out, and this is all ArcGIS. So this is partly why we keep Africa fixed in the same place, because then you can put a fault, and then you can look at literature and say, create an attribute and saying fault active Pliocene, fault active Miocene, fault active Eocene, and then you can manipulate your attribute table to only display faults which are active in a specific period. So that, for instance, is how the tectonic elements and all the rifts are. Obviously, from the plate tectonics, Colin's done everything for me, and obviously he's got decades of work in there. Volcanics, a similar thing. You can there's a USGS shapefile for the outcrop of Africa. From that, you can extract all the volcanics, and it's already got some dates in there, but you can research the literature and again do your columns and say, well, that's an Eocene volcanic, that's a late Cretaceous volcanic, etc. And then make just only show the late Cretaceous volcanic. If you're doing a late Cretaceous map, you can only show the late Cretaceous volcanics. And the same with paleoclimate. There is a wonderful atlas which I actually got. It's it's not in the Geological Society at the moment because I've got it, which actually maps out all the evaporites and maps out all the bauxites of the world. Obviously, find more. Have to do a little more research on the ages again. That can form, and then you can go through all the literature. I did a search, just basically an Adobe Acrobat search of papers which had the world paleoclimate in, and copied out. You know, this says Egypt was tropical in the Eocene. So again, attribute table for that. So an awful lot of attribute tables in GIS. It couldn't be done this fast without GIS.
Do you think, you know, using the subject of GIS and these modern technologies, is there anything in the future where you see that's emerging now that would be really helpful for the research to develop in areas that you maybe are missing those key bits of data?
Yeah, the key, obviously the thing is in artificial intelligence. My daughter's into that. So I think the problem is that most of the work is compiling the database. If you can get something to go through 2,000 papers and find the world climate or paleoclimate and extract where it was arid, where it was hyper arid, where it was humid, you'd be onto something there. I don't think we're too far away from that. I mean, obviously, I'm a bit old for this, but I have seen things like that done. I guess a lot of perhaps the problem is that actually when you go back to the last century, things haven't been digitized. I mean, most of the papers, and an awful lot of the best papers in Africa are quite old. You sometimes have to go back to some very old literature which hasn't even been put into a PDF yet. So there's things you might miss, but yeah, I think there are things artificial intelligence could do here.
Hey Duncan, it's Tom here. Good talk. Quick question. You talked about volcanic poor and volcanic rich margins. Now, I've seen a couple of talks in some of the recent conferences that are kind of talking about intermediary and different changes and where the cob limit sits and such, you know, looking at mechanical strengthening, mechanical weakening. Do you notice any trends around that, around the African margin, or any larger scale buckets?
I think probably not, I would say. I would say the volcanic areas are actually these light purples. So this Namibian margin, this Mozambique margin, Seychelles, and bits up here as well of Gabon, which I've not shown there. And there's a bit of debate of this margin because people think the North American margin is volcanic, but I don't see too much evidence for on the African side, albeit poorer. So that's what, and actually the thing, they actually change very rapidly. You go from here in the Walvis Basin, maybe 13 kilometers of volcanics. You go down in the Mabi Basin, yes, you still got them there, but they're much thinner. They actually change pretty rapidly to a hyperextended margin. So I guess I would perhaps say, yeah, I mean, they're surprisingly categorical with quite limited areas of transition. I can't get to the, for some reason I can't get to the, all right. Let's see if there's any in the chat box, our chat, right?
I can't see any questions in the chat box, but just
okay.
Thank yous and appreciations for your talk. So if it's okay with everyone, then I will stop recording. But just thank you.
Yeah. I mean, this is all on the. If you want to see any more of this, so all the time slices that are missing, this is all in 2 websites. The plate tectonics is Earthworks. Actually, if I go back to the start, Earthworks, if you Google that, if you want to see my maps with all the climate and the interplate tectonics and things like that, actually screen shaving has stopped that. You go to geology. So my name, but just geology instead of Gregor. So obviously I've that's the name of my very name for my company. Unfortunately, no one had ever taken that name. So what was the problem when you started a company, finding a new name? But that was easy for me. Okay.
Thank you.